A direct proof is a method used to show that a statement of the form if P then Q is true. So what is the strategy here? First, we assume that P is true, and then we use logical steps and theorems and known definitions and axioms to show that Q must also be true. So to show Q is also true. Let's see a couple of examples. First one, we must prove that if n is an even integer, then n squared is also even. So the first thing we should do is try to recognize the type of proposition that is being given to us. Is this an implication? So do we have a P implies Q here, if P then Q? Yes, we do, right? We're trying to prove that if n is an even integer, so this is P, then n squared is even, and this is Q. So we have a statement of the kind if P then Q. This does not mean that necessarily we can use a direct proof to prove this, but it shows that we can at least try. So we start by assuming the hypothesis, which is n is even. This is our P, it's our hypothesis. N is an even integer. So we are assuming it, right? We're assuming n is even. Since n is even, we can write it as 2 times k, k being some integer, because every even integer is a multiple of 2. And if n equals 2k, then n squared equals 2k squared, which equals 4k squared. And this is also an even integer. We can write it as 2 times 2k squared. It's a multiple of 2, so n squared is also even. And that's it. We've shown that if n is an even integer, then n squared is also an even integer. This completes the proof, and we can use this little square here to indicate that. Now let's try a slightly more abstract one. We want to prove that if a and b are rational numbers, then a plus b is also rational. So again, we have a proposition of the kind if p then q. What is p here? A and b are rational numbers, and what is q? A plus b is rational. So again, we're going to start by assuming p. So in this case, we will assume that a and b are rational. Now the little trick here is, how can we write a rational number? Well, if a is rational, then it can be written as p over q, where p and q are integers and q is different than 0. Same thing for b. b can be written as r over s, where both r and s are integers and s is different than 0. So p, q, r, and s are all integers, and q and s are not 0. Cool, this is our assumption. So now we're going to do a plus b, which is going to be p over q plus r over s, which is going to be ps plus rq over qs. Now again, what do we know about these four numbers here? P, Q, R, S. We know they are all integers. And we also know that Q and S are integers that are not equal to 0. So this must be a ratio of 2 integers and the denominator is not 0, which means that this is a rational number. So if A is a rational number and B is a rational number, it follows that A plus B must also be a rational number, which is precisely what we wanted to prove. As I said before, a direct proof is usually the simplest method when it works, but not all statements can be proven directly, so that's when we consider other strategies like contraposition or contradiction. But when the path is clear, do go direct.